Oh my gosh. Hello. I'm in a room with Hazel, and she is doing some pretty epic farts in here. Um, gonna wait for a couple more viewers. Ugh. Tell you what, class, today is just not my day. I feel very low today. My emotional cup is not very full today. Let's see if I'm at 15 yet. We're going backwards. We're at 7 people. We're supposed to be at, oh, now we're at 10 people. Do Wolfden every day. Hey, did you use the string reverse method to do Ole? All right, I'm just going to get started since we're already 3 minutes late. So we have to start out class with a little bit of mathematical preliminaries. So yeah, some mathematical preliminaries. I have avoided this up until this point because we didn't need it until now, but now there's no avoiding it. We have to learn about something called integration. Okay. So we're only going to do the most basic integrals. If you've never seen integration before, you're going to be fine. Okay. This is for you. I'm going over this for you. All right. If you've never seen an integral before, I'm specifically going over this for you, so you need to pay attention. If you've already taken calculus, you know that what I'm showing them is ridiculously easy. And so if you know someone who's in this class who has not learned integration yet, you tell them, you send them a message, and you say, I know you can get this. This is like not very tough at all. Okay? It just sounds scary. Integration is the reverse of differentiation. Okay? And so when you do an integral, it has a special symbol. Okay? So the special symbol is this. It's kind of like a stretched out S. Actually, it is a stretched out S. That's where it comes from. Okay, so you start out with that symbol. That's the symbol for integrating, just like ddx is the symbol for differentiation. For integration, you start out with this symbol, and then you would write down the function that you're going to be integrating. So maybe my function is 4x to the 9th. Okay, and then you put dx, where this So this right here is the function that you are integrating. And you can see it's a function of x. So I put dx after that. Okay, so it's this is telling us what is the variable that we are integrating with respect to. It's possible to have functions of more than one variable, so you need to specify which function you're integrating with respect to. And so the rule is you keep the constant, you bump up the power by 1, because it's the reverse. Remember, when we differentiate, we reduce the power by 1. When we integrate, we bump up the power by 1. So we have x not to the 9th power, but to the 10th power. And then, remember how we multiplied by the power, okay, when we differentiated. In integration, we divide by the bumped up power. So we divide by 10. So 4x to the 10th divided by 10 is that integral. Okay? So this is for a monomial. Monomial meaning just a single term polynomial. Okay? If you have more than one term, you just integrate each of them separately and add them together. Okay? So for example, if you had the integral of, let's say, 3x minus 5x squared dx, then we're going to do the first integral and then the second integral. Okay? So the first one, remember, if you just have x by itself, that is x to the 1 power. Okay? X to the 1 power. So bumping up that power is going to give me x squared. And then we divide by the bumped up power. So we divide by 2. All right? Minus 5 times x, and I bump up the power, x to the 3rd, and then I divide by the bumped up power. Okay? So that's how you integrate a polynomial. One important thing is if you have a constant, if you integrate a constant, like let's say we integrated 7 dx, well, we can think about this as 7 times 1, which is the same thing as 7 times x to the 0 power. Okay, so bumping up that power is going to give us x to the 1 power, so 7x, and then we divide by the bumped up power, which was 1. Okay, so these types of integrals, these three types of integrals, are what are called indefinite integrals. Okay, indefinite integrals. Now, okay, there's another type of integral. It is called a definite integral. So a definite integral, oh my gosh, is this? It looks the same as a regular integral. Okay, so maybe I do 5x to the 8th dx integrated, and so where the difference comes in is you have what are called the limits of integration. So for this particular example, we are going to integrate from 1 to 2. Okay, and so what you want to do is you want to start off by just doing the integration like it were an indefinite integral. So we're going to bump up the power by 1, 5x to the 9th, Then we're going to divide by the bumped up power. Okay? And then I'm going to put a little line right here, and I'm going to write 2 and 1 just to remind myself that those are the limits of integration. Okay? So now what you want to do is you want to take this function that is the indefinite integral, and you want to plug in the top number into that function, and you want to plug in the bottom number into that function, and then you subtract the two. Okay? So we have 5 times 2 to the 9th divided by 9. So that's the top number plugged in. The bottom number plugged in, 5 times 1 to the 9th over 9. And we take those top number minus bottom number, so we subtract them. All right? So this is my little introduction, my mathematical preliminaries for that we'll need for this lesson. Okay. Work is the topic of today's lesson. Work is denoted by W. Okay. And work is the integral of the force as a function of position. So this is the force as a function of position from the initial position to the final position. Okay? So it's a definite integral of the force with respect to position. That is work. So that is the main equation for today. The units of work are joules. Okay? The units of work are joules. So let's do an example. Okay? So, and by the way, I hope it is clear that work is very closely related to potential energy, because you might remember that, so I'll just write over here, that potential energy is minus the derivative of the potential energy is force. So that means that potential energy is minus the integral of the force. Okay? So what is the difference between work and potential energy? Well, first of all, potential energy is an indefinite integral. Work is a definite integral. And then you also have this minus sign here. So they're very closely related, but they're not quite the same thing. Okay? So I'm just going to separate that. All right. So what if we have a force as a function of position that is given by 3x? Okay? We want to calculate the work done by this force as the particle goes from x equals 1 meter to x equals 3 meters. Okay? So 1 meter is the initial position of the particle, and 3 meters is the final position of the particle. So in this case, the work is going to be the integral, and it's a definite integral from 1 to 3 of the function 3x dx. So how do we do this? Well, we do the integral just like we would normally. So this is actually x to the 1 power. So we bump up the power, 3x squared. Then we divide by the bumped up power, divide by 2. And this is a definite integral, so I'm going to put my line here to remind me to plug in 3, plug in 1, subtract them, okay? So now I plug in 3 into this function. I get 3 times 3 squared over 2. And then I plug in 1 into this function. I get 3 times 1 squared over 2. And then I subtract them. So 3 cubed is 27, minus 3 is 24, and then divided by 2 is 12. So the amount of work done is 12 joules. Okay? So that's a nice little example. Let me, okay, so work can be done by a single force. So single forces can do work. Okay? This could be a single force. Also, the net force can do work. So, you know, I didn't say that this was the net force. This was a force. Okay? This was a force that is acting on the object. But if it were the net force, we would call it the net work. Okay? So the net, not one word, this is two words. The net work, which is denoted by W sub net, is equal to the work done by the net force. So net force dx. All right, so that's important. And there's a really nice theorem that I'm not going to prove, okay, and I'll explain why in a second, that explains why we talk about work in the context of energy, all right? So that theorem is called the work kinetic energy theorem. Okay, and what it says is that the work done by the net force is equal to the change in kinetic energy of the object. Okay, so this is what relates work to energy. It's kind of the proof that work results in changes in energy. When we were worrying about work last year, I just said work is a transfer of energy from one system to the other. And so this is the formula that really connects the two. Okay? So please, please, please be careful. This theorem only applies if we're talking about the work done by the net force. Not an individual force, but all of the forces together. The work done by all of the forces acting on the particle together result in changes in kinetic energy. Okay? All right? So let's do an example that applies the work kinetic energy theorem. Suppose the net force as a function of position is given by 3x. So it is the same function as last time, only this time I said it is the net force. Okay. Suppose a net force of blah acts on a 2 kilogram particle that is moving from x equals 1 to x equals 3 meters. Okay? It starts at x equals 1 with velocity 2 meters per second. So that's the initial velocity of the particle. What we want to know is, what is its velocity? At when it arrives at x equals 3 meters. Okay? So we are going to apply the work kinetic energy theorem to this problem. Okay? So net work equals change in kinetic energy. This is the exact same problem as before as far as calculating the work is concerned. So I can immediately say that the net work is 12 joules because that was the answer that I calculated in the previous problem. Okay. So this is going to become 12 equals 1, and that's going to be 1/2 times the mass, which is 2, times v final squared, minus 1/2 times the mass, which is 2, times the initial squared, which is the initial velocity is 2 meters per second, so 2 squared. All right. So I have 12 equals v final squared minus, and this is 1/2 times 2 times 4, so that's going to be just 4. I add that to the other side, I get 16 equals v final squared, which says that 4 meters per second is v final. So once the particle arrives at x equals 3, as a result of this force, it's going to have that much speed. So it actually sped up a little bit. It went from 2 meters per second to 4 meters per second. All right? So this is how the work kinetic energy theorem is how a the work kinetic energy theorem is how, oh my gosh, oh, it was bugged this time to release the fart. I got 12 from the previous problem that I did because it was the exact same force in the exact same initial and final positions. So I just said that, so the answer is just 12. All right. So this formula that I gave you right here, this is the definition of work, okay? But I want to give you an alternative interpretation of work. Alternative interpretation of work. So let's suppose that you have a graph of force versus position. Okay, so maybe this is what the graph looks like. The particle has an initial position and it has a final position. Okay, the work is going to be the area under the curve between those two positions. All right. So that's an alternative interpretation of work. So actually in last year's class, when you guys were doing area under the curve, you were actually doing integrals without, definite integrals without knowing it, okay? So those are the same thing. So I wanted to give you that little interpretation. So that's important. So now we have sort of one more topic here. The previous examples involve one-dimensional motion. Okay, so we have a particle that is moving along the x-axis only. Okay, so the question is, well, what if the force and the displacement do not point in the same direction? Okay, in that sort of a situation, so we have a part of we have a force vector which points in some direction, so maybe that's our force vector. So because this is inherently two-dimensional, I now have to worry about vector notation. And then I have a displacement that points in some other direction. And when we were talking about displacement as a vector, we called it delta r. Okay, so in this kind of a scenario where the force and the displacement are not in the same direction, the definition of work is force dot product displacement. Okay, so force or work is a dot product. This is essentially the whole reason why we learned dot product, is so when we got to work, I could write down that formula. Okay. Work is force dot product with displacement. So just to remind you about the dot product, there were sort of two ways we could think about the dot product. One way to think about the dot product would be to do, say work is equal to magnitude of the first vector, so magnitude of the force, times magnitude of the second vector, magnitude of the displacement, times the cosine of the angle between the two. So that was one interpretation of work, or of dot product, okay? Another interpretation of dot product is to do x component times x component plus y component times y component. So x component of the force is F sub x component of displacement is delta x, plus y component of the force, which is called F sub y, times y component of the displacement, which is delta y. Okay, so these are two alternative. So if you forgot how to do dot product, then these are some equations to help you. Okay. All right. So let's do an example. Actually, two examples. Our first example is an inclined plane of angle 30 degrees and length. So I guess I should say we have an inclined plane of angle 30 degrees and length 11 meters. Okay? It has a 2 kilogram block at the top. The coefficient of kinetic friction between the block and the incline is 0.1. What is the work done by the friction force in that case? All right. So I'm going to draw out this scenario. It's a 2 kilogram block. Okay, 30 degrees. The coefficient of kinetic friction is 0.1. So I'm going to be using this first form of work. Okay, so the magnitude of the force, because I want the work done by the friction force, I'm going to do magnitude of kinetic friction times magnitude of the displacement times the cosine of the angle between them. Okay. So first thing I have to do is I have to get the magnitude of the friction force. And we've already had an inclined plane lesson. So I assume that you already know about inclined planes. Okay. And one of the things, so I assume you already know how to calculate kinetic friction on an inclined plane. One of the things that that I didn't teach you is I never just gave you the formula for kinetic friction. I have the formula in my head for what kinetic friction on an inclined plane is, but I didn't give it to you because I know why that equation is true. But if I told you that equation, then you would just write that equation down and you would never understand why it is what it is. But it turns out that friction on an inclined plane is mu mg cosine of theta. Okay, where theta is we got to be careful here. This theta represents the angle between the two vectors. This theta represents the angle of the incline. Okay. So mu is 0.1. It's a 2 kilogram mass. Gravity is 10. And then we have cosine of 30 degrees. So the magnitude of the friction force is 0.1 times 2 times 10 times cosine of 30 is about 1.7 newtons is the magnitude of the friction force. Now, so that's this. The magnitude of the displacement, well, the incline has a length of 11 meters, so it's going from the top to the bottom, so it's traveling 11 meters. Okay? All we have to do now is figure out what is the angle between kinetic friction and displacement. Okay? And as this block is sliding down, the displacement is going to be along the incline. And friction points in the opposite direction, right? Because it's an oppositional force. So the angle between those two vectors is actually 180 degrees. If two vectors are parallel, the angle between them is 0. If they're anti-parallel, you have to rotate one by 180 degrees to make it point in the opposite direction. So anti-parallel vectors have an angle of 180 degrees between them. So this gives a work done by friction of 1.7 times delta R, which is 11, times cosine of 180. Now, cosine of 180 is actually -1. Okay, so we have 1.7 times 11 times -1, which is negative 18.7 joules is our answer. Okay? Now, what does that mean? Thinking back to the work kinetic energy theorem. Because friction does negative work on this block, even though it's just one of several forces acting on the block, its contribution to the net work is going to tend to reduce the kinetic energy of the block. So the fact that friction does negative work in this case is representative of this block is being slowed down by friction. Okay, it's being sped up by other things like gravity, but it's being slowed down by friction. All right. Let's go ahead and do one last example, which is to calculate in this same problem, what is the work done by the normal force? Okay, and this is actually really easy. Because if you recall, the normal force points perpendicular to the incline. So the normal force points that way. Because the block is sliding along the incline, the block is going in this direction. So we have normal force going this way. We have a displacement going that way. Okay, and the angle between them is 90 degrees because the angle to perpendicular to a surface and along a surface is 90 degrees. Okay, so that's our theta in the formula for work. So when we use this equation for work, force times displacement times cosine of theta, we're going to do the cosine of 90 degrees. Okay? And the cosine of 90 degrees is 0. So in most situations, the normal force actually does 0 work. Okay? There are some situations where the normal force does do work, and I'm going to wait about 30 seconds while I see if someone who can type it into the chat if they know a situation where the normal force does do work. Elevator, very good. So if you are on an elevator, okay, here's the elevator. Okay, and you're on the elevator. The elevator, the reason that you get moved by the elevator is because the normal force from the floor of the elevator pushes you upward. So you have a normal force that's going upward, and then you also have a displacement vector that is going upward. So the angle between them is not 90 degrees. So basically, situations where the normal force is doing work are situations where the floor itself is actually moving, okay? But if you have a fixed inclined plane, then it's not going to, or a fixed floor, then it's not going to do any work because you're always moving parallel to the surface. Okay, so that is my lesson for today, and I will see you in the Zoom room.